have x transpose u x plus u transpose r u dt. Now, a regulator is going to try to do what? Drive the states to what point? The origin? Zero. Yeah, the origin. So if I don't want to go to the origin, say my cruise control, I want to go 65 miles an hour, what do? Move the origin. So I can't have things like x minus x naught transpose q x minus x naught, like that, first before. Okay. Then there's some ways of defining these things in a bit. What I'm going to do is actually get to, how do I find the gains from this? What I'm going to do is derive what's called the Riccati equation. And doing it without variational calculus. This is a real trick. Actually, several ways of doing this. Classic variational calculus thing is the Hamiltonian method. We'll go back to Hamiltonians for that classes. It's an optimization method. And then kind of brute force, which we're going to do here. Here's our state equations. Same as we've always had. So with our controller, controllers will be the same. Right? So we can say this is some AC x, where AC is A and K. No difference. The difference is how do we find K? Now we're going to loosen this thing up. A and B matrix do not necessarily have to be fixed for this approach. They can vary. Look more general case. Imagine systems that might do this. Like an autopilot for an airplane or a rocket control. A matrix is changing due to what? You're burning off fuel. Mass is changing. Right? So my A matrix, B matrix might change around a bit. Don't have to be fixed. All right. Well, let's also remember what's P? Initial state, or state at some time t, times this phi equals the state at some other time tau. What's phi? State transition matrix. We talked about these things. We use for calculating this. All right. Nice thing about this is that for a state transition matrix, x is going to x tau varies linearly with xt, idea of the state transition matrix. So let's put this into our performance index. Here's our performance index. And I'm going to go from t to tau for our time. And it's x transpose tau q x tau plus u transpose r u d tau. U is? U is B times K X. But then, now when we take the transpose of BKX, what's the rule in linear algebra for that? It's in terms of the transpose of each one. Reverse the orders. X transpose, K transpose, B transpose. I remember your linear algebra here. There's rules. Okay. So this is X transpose, K transpose, R, K, X, it's tau, D tau. I'm integrating over tau, so the initial state of X isn't part of the interval. So I can pull it out. Initial state of function tau, so it can come out. So I can have two parts, which is this. And this M. Oh, we can do a bit of transpose tau T on Q plus K transpose RK times V as a function of T D tau. Right. So I'm using our state transition matrix to define what X of tau is. Right, so I'm using state transition matrix for the closed loop system to take care of what X is, X of tau. And this M is a symmetric matrix. Obviously this thing right now. And what we want to do is to find the differential equations that satisfy M of T tau. And V is a function of the initial time. Let's see how we solve this. What I have now is V interval tau, sorry, of X transpose tau. I'll call it tau of tau. I can rewrite it this form. So if I differentiate V with respect to time, that's simply going to be, well, integral this thing, so it's simply minus d transpose x transpose. Tau L x tau evaluated tau equals t, which will be minus x transpose t L x t. Keep that equation.
What's L?
What's that?
What's L?
L is another function right out here. I'm defining that you have another function here. We'll see what's out. Right? Keep that one handy. We're going to use that in a bit. Basically taking, I can write this as some function, L. We'll see what that is in a bit. Derivative of that with respect to that, since it's integral of that, it's got to be just what's inside. And look at the M equation. Kind of write the same sort of thing here, right? And then we're going to write these L's and M's. So we're kind of taking two approaches, and we're going to equate them. So from this V equals x transpose mx, this. So to take derivative of this, I need to take derivative of each part of it. And m dot, in this case, means the partial of m, which is function t and tau, with respect to t. Partial derivative of m with respect to t. All right. Then what we're going to do is put in the state equations. Put in the state equations, you get like this. Of t. Don't worry, I won't write all these T's and tau's and such things. And so I have two equations, this one and this one. Let's put them together. That says minus L equals transpose of the closed loop A matrix times M plus M dot plus M times closed loop A matrix. Or I can say minus M dot equals M AC plus AC transpose M dot L. Curious thing here is that the M with T equals T, tau equals T, something out of here is equal to 0. The final time M goes to 0. So if you think about this, in the final time, the final condition, we're going to use it as an initial condition. How do we do that? How do we make a final condition an initial condition? Don't think too hard, Zach. We'll real simple. One of the things, calculate the differential equations backwards. So instead of going forward in time, you start to find the time to work backwards. Solve the problem backwards. So solve it backwards and join. All right. Well, almost there. I have this A closed loop. Let's put in the A, B, C, K, U, everything else into this thing. All of our state equations parts. So we're going to put in the A, the B, the K, which we're going to try to solve for here, and our penalty function is Q and R. Right? So this is the open loop A, open loop B. This is what we're going to try to solve for. Right? And then what we've defined as Q and R. Put all that stuff in here. You're going to get this. Our AC is A minus BK, of course. Transpose of that. Q. Now. Rearrange things, do a bit of algebra, and you can get down to that. Right? It's a few steps I skipped in that, but you can put in all those values, you can get down to this. All right, well, when I want to find this, I want to find K. That's what we're after. And what we're going to try to do is we're going to try to find K that makes the solution, if you will, it's a differential equation, so the solution is M, as small as possible. Because we make it M as small as possible, I believe B as small as possible. All right, well, let's see how we do that without doing variation calculus. Hamilton's method. And the premise of it is quite simple. There should be, let's say this is the optimal V, the minimal V, I'll call it V hat. This is kind of the minimum V. And it's going to be some state, transpose, some minimum M times the state. And that must be less than some other value of M. Right? Well, the idea is that M hat is smaller than M. Okay, so a lot of methods to do this. Let's do the following way. So if I have this M hat, well, that is going to everything here.
Hey, quick question.
Yeah.
Is this supposed to be X prime or X transpose?
Transpose, I'm sorry, I'm using MATLAB code here. Right. Whatever, if you see it probably means transpose, think MATLAB. Okay, so I have this same thing here, is